Hello friends, welcome back. This is the second part of the video on 3D equilibrium of rigid bodies, and in this part I'm going to show you how summation of moment about an axis can be used in solving certain equilibrium problems. In the previous problem, we implemented these two equilibrium conditions. We wrote the equation sigma f equal to 0 and sigma ma equal to 0. That is, we computed moment of all the forces about a point A, and we chose point A so as to eliminate maximum number of unknowns. Now, most of the equilibrium problems are solved by implementing these two equilibrium conditions, but there is another category of problems which can be quickly solved by using this equation sigma mb equal to 0, where AB is an axis, and this methodology is effective when only one unknown is to be calculated. To clarify the point, let's take a look at this figure. What you see here in this diagram is a L-shaped plate which is acted upon by a force of 100 newtons at point D and is supported by ball and socket joints at corners A and B and just a ball on a horizontal surface at C. And we are interested in finding out the reaction at point C. Since this support is just a ball which prevents motion in vertical direction, the reaction here will be just a single force component in vertical direction. But here, these are ball and socket joints. There would be three components of reaction forces pointing in x, y and z directions, and similarly there will be three force components acting here. As you can see here, we are interested in finding out only the magnitude of this reaction at point C, and these are the reactions at point A and B. We are not interested in finding out the values of these reactions, and therefore if we take moment about a line AB, then these reactions get eliminated from our equation, and our equation will have just one unknown, and therefore it makes sense to compute moment about an axis AB. This aspect will be more clear when we solve a problem. Okay? So here is a problem that we have to solve. We have a rod ABDE which is supported by ball and socket joints at E and A. There is a cable DF and there is a external load of 300 newtons at point C, and we have to find the tension in this cable. The first step obviously would be to draw a BD of this rod, and that will look like this. The tension force T would be pointing towards F. Because of the ball and socket joints at A and E, we shall have three force components at E and A. The problem does not say that we have to find out these reaction components. The problem says that we have to find only this tension force. So it makes sense to compute the moment of all the forces about an axis, this blue colored axis which passes through points A and E, so that these black colored reaction forces at E and A would get eliminated from our moment equation, and our moment equation then will have a single unknown T, and we'll be able to compute the value very quickly. This is an important point. Okay? So before we write the moment equation, let's find out the force T in vector form, and that will be equal to the magnitude of the tension T times a unit vector lambda df, and lambda df is equal to the position vector rdf divided by its magnitude, and rdf is minus 400 I 275 J and minus 200 K. And in the denominator you have the magnitude of this position vector, and this will simplify to this vector. And therefore, the tension force would be equal to T upon 21 times this vector. So this is the tension force in vector form. We shall also need a unit vector along the axis EA. Let's call it lambda EA, and that will be equal to position vector REA divided by its magnitude. And REA is minus 600K plus 175I divided by 625, which is the magnitude of REA, and this will simplify to this. So this is the unit vector along the axis EA. Okay? So as I said before, we shall be computing the moment of different forces about an axis, and that axis is EA, and we have chosen this axis so that the reaction forces at A and E get eliminated from our equilibrium equation, and therefore we shall have to compute moment of just these two forces, T and the 300 Newton force acting at C. The first term is the moment of force T about the line EA, and this term is the moment of the 300 Newton force about the line EA, and the sum of these two moments is equal to 0. I had covered the moment about an axis in great detail in my video, the link of which I am providing below in the discussion section. And if you are not familiar, I would strongly suggest you to first watch that video and then come back here. You will make the most of this video. So the procedure to find out the moment about an axis is to first choose a point on the axis, and in this case we have chosen the point E. So first we compute the moment of force T about point E. So this is the moment of the force T about point E, and then we do dot product of this vector and the unit vector along EA to get the moment about the axis EA. The same procedure we follow for the 300 Newton force. The position vector REC crossed with the force vector will give the moment of this force about point E, and then this moment vector is dotted with the unit vector along the line EA to obtain the moment of this force about this line. So we now have this equation, and we expand it by determinant method. Perhaps you are looking at these determinant for the first time. So let me explain this in a separate slide, and then we will come back here. We are interested in computing the moment of a force about an axis, and the procedure involves two vector operations. One is R cross F, and then we dot it with a unit vector lambda. So when these two vectors are dotted, they give us the moment of the force F about the line OL. So we want to perform these two operations, first a cross product and then a dot product. So there are two ways to perform this computation. One is a two-step process in which first we compute the cross product of R and F by determinant method. So the first row we write ijk, the second row we have the position vector components, and in the third row we have the force components. And we know how to expand this, and this is the expanded form. So this is the moment about point O, and next we carry out the second operation, which is we carry out the dot product of lambda with this vector MO. Lambda is given here. So when we do the dot product, we multiply the I component here with I component of lambda plus the j component of this vector with j component of this vector plus the k component of this vector is multiplied with the k component of this vector, and the result is this. So this is the moment of the force F about the line OL. Now the same result can be obtained from a single operation. So this is a shortcut method in which we again write a determinant. The only change that we make now is that instead of writing ijk in the first row, we write the components of our unit vector along the line OL. So we write lambda x, lambda y, lambda z. The second and third row entries remain the same. That is xyz and fx, fy, fz. And when we expand this determinant, we get lambda x times y fz minus z fy, which is the first term here, and so on. So we notice here that the result is same as what we got here. So this is not a new concept. This is just a shortcut of performing two-step process of first cross product of two vectors and then dot product with third vector. The same operation can be done in one shot. This is what we are going to use in our solution. Okay? So I'm going to use the shortcut method in expanding this equation, and the components of lambda EA will come in the first row of the determinant. The second row and third rows would be occupied by the position vector and the force vectors. 7 by 25 will appear here. There is no j component in lambda EA, therefore we'll have 0 entry, and minus 24 upon 25 will come in the third column. The same will get repeated in the second determinant, and here will be RED components. Here we shall have REC components, and these are the components of T, and these are the components of the 300 Newton force. Okay? So we shall now expand these determinants, and we get this equation. And notice here that there is only one unknown, that is T. And therefore it is going to be fairly easy in computing the value of T. So by simplifying this equation, we get T equal to 426.56 or 427 newtons. So, and that is our answer. So you notice here that in few steps we are able to compute the value of tension force by considering moment of the two forces about the axis EA. So I hope you found this tutorial useful. In case you liked it, please give your thumbs up, and if you are new to the channel, please subscribe it. Thanks for watching, and see you next time.